All right, so the second subsection under the special continuous probability distribution is the exponential distribution, okay? All right, so the exponential distribution is a special case of the gamma distribution when we set alpha to be 1, okay? The exponential distribution describes the time until the occurrence of a Poisson event or the time between Poisson events, okay? For instance, the time before an earthquake strikes in a certain region, or the time it takes to get a new customer, or the time interval between telephone calls at a certain switchboard, okay? Similarly, in waiting time studies, the exponential distribution can be used as a model for the time until failure of an event, okay? So other applications of the exponential distribution include survival times in biomedical experiments, insurance risks, and computer response time. Let's take a look at the definition for exponential distribution. The continuous random variable x is said to have the exponential distribution with parameter beta if its PDF is given by equation 2.21. If you can record the PDF of the gamma distribution, you realize that once we set alpha to be 1, we obtain this special case of the gamma distribution, which is called the exponential distribution, okay? Let's take a look at this remark. The CDF of the exponential distribution is given by equation 2.22, and by now, I guess you know how to compute or calculate a CDF of a random variable. In case you don't know how to do this, you can check out my video tutorial on CDF by clicking on the link in the card above, or check the description below this video for the link, okay? All right, so let's take a look at this graph. We have the exponential probability density functions for selected values of beta. Okay, so when alpha is 1 and beta is 1, this is how the exponential distribution look like with exponential decay. Okay, when alpha is 1 and beta is 2, we also obtain this. Okay, all right. So let's take a look at some properties of the exponential distribution. If x has the exponential distribution with parameter beta, then the expectation of the random variable x is equal to beta. We have the variance to be equal to beta squared, and we have the moment generating function to be 1 divided by 1 minus beta multiplied by t, okay? Where t is not equal to 1 out of beta. All right, so let's take a look at this theorem, lack of memory property. If x has the exponential distribution, then for any positive numbers t and s, the probability that x is greater than t plus s, given that x is greater than t, is equal to probability that x is greater than s, okay? So what does this theorem entails? So this theorem basically means that, or states that the exponential distribution has no memory, okay? So for instance, let's assume that this random variable x, let's assume that this random variable x is the lifetime of some device, okay? And let's assume that this device has lasted for a period of length t, okay? So the probability that the device will last at least s more time unit does not depend on t, okay? Which basically means that the remaining life of the device does not depend on how long it has been used, okay? So therefore the device is as good as new, okay? So this is basically the intuition behind this lack of memory property, okay? So there's a proof to this theorem. Let's take a look at the proof. For any positive number t, probability that x is bigger than t can be expressed in this form, okay? So once we take the integral of this, we obtain this, okay? Where we replace 1 out of beta, that's the rate with lambda, okay? So we obtain this. So we know that the probability that x is greater than t plus x, given that x is greater than t, can be expressed in this form based on our knowledge on conditional probability, okay? So we want to find the intersection here, and we know that this side is embedded in this, so we obtain this to be the intersection. So based on this definition that we have here, we can express the numerator in this form, and the denominator can also be expressed in this form. So once you work this one out, you obtain this result, which is similar to this, which ends the proof, okay? All right, so now let's take an example. Suppose the time it takes university graduates to get employment is exponentially distributed with mean 2 years. We want to find the probability that Ishmael, who just completed the university, will get employment not earlier than 3 years, and secondly, between 1 and 2 years, okay? So let's take a look at the solution. Let x denote the time it takes university graduate to get employment. So the PDF of x can be defined as shown below. Of course, here we have the mean to be 2, so the rate will be 1 out of 2. Okay. So we are required to find a probability that x is greater than or equal to 3. Okay, so we want to find a probability that, let me take a look at it. We want to find a probability that Ishmael, who just completed university, will get employment not earlier than 3 years, which is similar to x greater than or equal to 3 or at least 3. Okay. So this can be expressed in this form. Okay. So once we take the integral, we obtain this. Once we input the values, you obtain that, which is approximately equal to that. So there's approximately 22% chance that Ishmael who just completed university will get employment not earlier than 3 years. Okay. All right. So let's take a look at the second part. We are required to find a probability that Ishmael will get employment between 1 and 3 years. So this can be expressed in this form. Okay. Once we take the integral, we obtain this. Once we input the values, we obtain that. And this is approximately equal to that. Okay. All right. So another example. A random variable y has the moment generating function given by the equation below. We want to find a probability that y is less than 1 out of 3. So let's take a look at the solution. We know the moment generating function can be expressed in this form, which can also be expressed in this form. You can see that this is similar to the moment generating function of the exponential distribution. So beta is equal to 1 out of 3. Okay. So therefore, we can have our PDF defined in this form. So therefore, the rate is going to be 1 divided by 1 out of 3, which will give us 3. Okay. All right. So we want to find a probability that y is less than 1 out of 3, which is equal to the cumulative. And we know the cumulative with exponential distribution to be given in this form. So we replace this value, which is the particular value of y in here. So once we compute this, we obtain this, okay, which is going to be the solution. All right, so this will be a trial question. I will leave the solution in the description of this video so you can check it out. Please, if you find value in today's tutorial video, don't forget to subscribe if you have not, and thank you for watching.